Hello everyone, my name is Caleb Robinson and I'm a data scientist at Microsoft's AI for Good research lab. I'll be presenting our work on detecting cattle and elk from high-resolution satellite imagery, which was done in collaboration with our partners at the Smithsonian Institute. So to motivate this work, we want to answer why do we care where cattle are and why are we using satellite imagery? One really important reason is that being able to do cattle surveys over large areas lets us study phenomena like the Serengeti-Mara squeeze. And finding cattle in satellite imagery with automated approaches enables us to perform these surveys over large areas. For some background, the Serengeti-Mara ecosystem is a 40,000 kilometer squared area, which is about the size of the US states of Maryland and Delaware, and home to the largest mammal migration paths on Earth. Millions of wildebeest, gazelle, and zebra make a huge 800-kilometer trip through it twice a year. And you can see here that this results in some stunning scenes. The squeeze is the term given to the human activity around the borders of this ecosystem. For example, farmers slowly moving their cattle into the protected areas and disrupting wildlife. If we know where cattle are in relation to this ecosystem, we can determine where the squeeze is happening, i.e. where farmers are encroaching and how it might be changing over time. Now, from a machine learning standpoint, performing these surveys can be cast as a computer vision problem. Here you want to train a model that takes high-resolution imagery as input and either localizes the animals in the image, solving a segmentation problem, or simply counting all the animals in the image. Then you run this model over large amounts of imagery and summarize the results to get a survey. And as an aside, to detect cattle or elk, you'll need imagery with a spatial resolution of at least 0.5 meters per pixel, which currently is available from commercial satellite imagery providers. The WorldView or 3 satellites, for instance, can capture panchromatic imagery up to 0.3 meters per pixel. This problem has been studied in several different research threads that look at detecting a variety of large animals in imagery. For example, there's this excellent paper on counting cows in high-resolution satellite imagery from last year's climate change workshop at NeurIPS. Here, the authors train models that achieve a mean average percent error performance between 20% and 40% on the task of counting cows in patches of imagery. However, they don't sample these patches randomly over some large study area and instead sample from locations near cattle ranches, so their results aren't applicable for evaluating how well the models would perform in survey settings. We aim to extend on these threads and more specifically do two things. First, think about how these models will be used and evaluate them accordingly. We measure the temporal generalization performance of models trained from data captured over a fixed location, and more on this in the next slide. And then second, we propose metrics for measuring the performance of models over large landscapes that take label noise into account, and in a way that will be more interpretable for domain experts. The dataset that we use for this study consists of 11 satellite imagery scenes from Point Reyes National Seashore in California. These scenes range from 0.3 meters per pixel to 0.5 meters per pixel and were captured from 2013 to 2018. The cows and elk in each scene were manually annotated with point labels, and in total there are around 10,500 labels. So this is what the study area actually looks like. This is about 30,000 by 30,000 pixels. One large problem in this dataset is that each label isn't precisely aligned with the corresponding object in the image. For example, in the image on the right, you can see that the label point is offset from its corresponding cow. And this is because this dataset was created by ecologists for studying the interaction of elk and cattle and not for the purpose of training a machine learning model. Nevertheless, we can repurpose this if we're careful about how we use the labels in both training and evaluation. Our first step in the modeling process is converting the point labels to segmentation masks appropriate for training deep learning-based models. We do this two ways. First, creating density labels by convolving a 7x7 Gaussian kernel with the point labels, and the resulting masks here are appropriate for training density estimation models. Second, creating binary masks by convolving a 7x7 maximum kernel with the point labels, and here the resulting masks are appropriate for training segmentation models. And the figure on the right just shows a partial example of what the segmentation binary mask looks like. The kernel size of 7 is important and encodes our assumption that the label noise should be less than 7 pixels, and we chose the value of 7 based on our preliminary experiments. We use these two different types of masks to train the following set of models. LCFCN, which is a state-of-the-art approach in segmentation-based counting, CowNet, which is the name we gave to a UNet with a multitask loss, a vanilla UNet, CSRNet, which is a density estimation model, and finally FCRN, which is another type of density estimation model. We evaluate our models with two different types of metrics, counting-based metrics and localization-based metrics. We calculate both of these types of metrics at a scene level, i.e. over a large amount of imagery at once, versus at the traditional patch level. For the counting-based metrics, we propose gridded versions of mean absolute error and R-squared. To compute these, you do the following, which is illustrated also on the right. First, create a grid over the scene with some resolution, for example, 1 kilometer sized grid cells. Second, compare the predicted counts to the actual counts over all grid cells, for example, using mean absolute error or R-squared. Then repeat this step with different sized grids. This allows you to create plots, like in the bottom figure, that shows how R-squared varies with grid cell size. It gives you an idea of how the model performs at the counting task at different scales, which is particularly important if you want to use the model in surveys. The localization-based metrics are a little bit more involved. Here we group contiguous sets of positive predictions into objects, and we want to compare these objects with the ground truth point labels that we have. The problem is that due to the label noise and the fact that our objects are very small, i.e. the cows and the elk, it becomes very easy to misclassify a prediction as a false positive or misclassify a label as a false negative. And we illustrate this on the figure to the right. If the yellow outlines are predicted objects and the green points are the labels, you can see that it is possible to correctly segment a cow in the image without having any overlap with its corresponding label. In another case, in the larger yellow oval, the predictions for multiple cows might be merged and cover two labels. To account for this uncertainty, we propose two methods for estimating the number of true positives, and false negatives, namely an optimistic method and a conservative method. The methodology for the optimistic method is pretty straightforward. First, we buffer each labeled point by some distance d. Then we calculate the true positives as the set of predicted objects that intersect a buffered point. The false positives are the set of predictions that don't intersect with a buffered point, and the false negatives are the set of buffered points that don't intersect with any predicted objects. Again, this is pretty straightforward, and we call it optimistic as a model that overpredicts the number of objects will not be penalized. Now for the conservative estimate, we apply the same logic. However, we enforce that each predicted object is paired with one and only one of the buffered labels. I'm not going to go into the details here, but you can compute this as the size of the maximum cardinality matching on a bipartite graph representation of the labels and the predictions. This is conservative because now overpredicting objects will be penalized. For instance, if multiple predicted objects fall within a single buffered point, then only one of them will be counted as a true positive, while the rest will be false positives. And on the other hand, if this happened with the optimistic estimate, they would all be counted as true positives. So now you can compute metrics like precision and recall over a variety of different buffer distances to get a better look into the true performance of the models. And this is what these graphs are showing for one of the models that we train. And you can see, for instance, a buffer distance of around 4 or 5 meters might be a reasonable choice, where the true precision and recall would fall somewhere between the optimistic and the conservative lines. Finally, on to experiments and results. We train on the first 7 of our 11 scenes, validate on the next scene, and test on the last 3 scenes, which lets us measure how well the models will generalize over time, given the fixed study area. Here we show the average test results over the 3 test scenes for the set of models that I mentioned earlier. The localization metrics were computed with a buffer distance of 4 meters, and the counting metrics were calculated with a grid size of 100 meters. The key takeaways here are that the LCFCN approach dominates the other models in the counting and localization metrics, and we find its performance to be quite impressive overall, achieving a precision of around 0.6 and a recall between 0.8 and 0.9. The purely counting-based approaches perform poorly with the 100-meter grid cell sizes, and by design, they aren't able to localize objects, which is why there are NAs in the table. Finally, the naive UNet approach oversegments the imagery, and in general, we find that all of the approaches have problems with false positive predictions. Here are the gridded R-square results showing the ability of the models to perform counts with varied grid cell sizes. A key point here is that the object-based models are performing very well at the larger cell sizes with R-squared values of over 0.8, which gives us confidence that they're able to actually be used for survey applications, which, if you'll remember, is how we initially motivated this work. Finally, to summarize, in this work we addressed the problem of detecting and counting cows in high-resolution satellite imagery. We proposed metrics for measuring the performance of deep learning models over large satellite imagery scenes with noisy labels, and we benchmarked the temporal generalization performance of several models. Thanks for your attention, and hope to get your questions during the live session.